So welcome, everybody. I'm super excited to have Michelle Park talk about the Vera Rubin telescope. Many of you are apparently hardcore fans of Kaipak and Stanford, so that's how you found out about this. So I'm glad you're here. I'll just tell you a little bit briefly about, I'm by training, I'm an engineer, but I love astronomy. So I joined the club and I'm super excited that I have for years now. And we've had a very long-term relationship with Kaipak and Stanford. And they provided a number of speakers over the years. This one in particular, I'm super excited about because Michelle, as I was reading her bio, at age 11, she already figured out what she was going to do. Most of us don't know that until we're at least 25. So, and she was reading a book about Pluto, is that right?
Yeah.
From a professor of my alma mater, which is Caltech. And although she loved the book, I hate the book because they demoted Pluto. And I have a personal conviction about that. So, but really, I'm super excited about the Vera Rubin. Those of you who have been following it, it's just came online about a year ago. And the images that are coming out are absolutely stunning. In fact, the quantity of information that's coming out of this is going to be overwhelming. So I'm particularly keen to hear as Sparks talk about how they're going to manage all that data. We're talking terabytes per day, is that correct?
Yeah.
Yeah, it's insane. In my work, we also handle terabytes per day, but usually it's more mundane aspects. So with that, I want to say thank you so much for coming, and it's all yours. Feel free.
Well, thank you so much for the introduction. Hello, I'm Michelle, and I wanted to start out today by starting with a quick little game. Describe that galaxy. So we're going to do exactly what Edwin Hubble did in the 1920s, which is to classify galaxies into one of three types: elliptical, spiral, or irregular. So take a look at this galaxy, and with a show of hands, does anyone think this is an elliptical galaxy? How about a spiral galaxy? Oh, that's an overwhelming majority. How about an irregular galaxy? All right, looks like spiral is in the lead. How about this galaxy here? Let's do this again. Show of hands. Elliptical galaxy? Spiral galaxy? Or irregular galaxy? There seems to be some debate over here. And finally, how about this one? This one's a little bit of a tough one. Elliptical galaxy, anyone? Or spiral galaxy? Or irregular galaxy? Oh, that is the overwhelming majority. Well, congratulations. All of you guys are all observational astronomers. What we did exactly now was one of the main missions of the Galaxy Zoo project, which is the largest citizen science project in astrophysics. This project, over the course of 15 years, asked over 500,000 volunteers a series of questions about these galaxies, just like how we did. They asked questions like, is the central galaxy smooth and rounded? Is the galaxy merging or disturbed? Or if you spot any rare features like a ring, lens, diffraction spikes, or more. The Galaxy Zoo project is considered to be one of the most successful citizen science projects, completing over 40 million classifications over 15 years. But the Galaxy Zoo project was important because it showed us how important these little galaxies actually are. So what is a galaxy? A galaxy is a system of stars, stellar remnants, interstellar gas, dust, and dark matter bound together by gravity. They are considered to be the fundamental building blocks of our universe. Just like how people in the planet live in cities, stars gather in galaxies. In fact, they are born, die, and their materials are ultimately recycled within these stellar cities. And so understanding galaxies can also help us chart a map of these stars in the universe. But galaxies are important to understand for many more other reasons. The first reason why is to understand what is the universe made of. It turns out that all of the matter that you can see and touch around you makes up just a mere 5% of the universe. The rest of the matter, not the 95% of that matter, is made up of the mysterious dark matter and dark energy, which we know very little about. Dark matter is called dark because it is literally invisible. It doesn't interact with the electromagnetic force, which means that we need to use galaxies and their shapes to help deduce where this dark matter is located. I'll be talking about this later in the presentation, so if you're excited, stay tuned. The second question is, how did the cosmos get built? We know that galaxies form by merging and assembling smaller galaxies over time. Therefore, for us to understand how galaxies assembled, we can then piece together how the universe assembled as well. The third reason why we need to know about galaxies is to understand what physics we are missing. One of the greatest mysteries right now is being posed by the James Webb Space Telescope. These are called the little red dots, or LRDs. They are some of the earliest galaxies in the universe, and we have no idea how they got this big and bright and why they look this way. This is showing us that there is something missing in our complete understanding of how galaxies form. And finally is probably the most personal question of all, which is, where do we come from? When the universe was born, it was only made up of hydrogen and helium. All of the elements you see around you, like carbon, nitrogen, oxygen that you're made up of, must have formed from the centers of stars. You may have heard the term, we are made of stardust. That literally makes sense because it turns out that these heavier materials were fused in the cores of stars. And when they died, those materials were then ultimately released and recycled in, you guessed it, galaxies. So these are four incredibly different questions, all answered by counting and measuring galaxies. This is exactly why we are designing large surveys to help understand these galaxies. To get you a sense for how powerful and how at scale these surveys can be, we can take a look first at the 1 million galaxies that were studied by Galaxy Zoo at the start of its project, over the course of around 2 to 3 years. These Galaxy Zoo galaxies were taken from a subset of over 100 million galaxies from our best surveys, specifically the Sloan Digital Sky Survey, or SDSS. But what if I were to tell you that there is another observatory just around the corner that will blow both of these out of the water? That is the Rubin Observatory, which is the topic of today's talk, which is going to look at a whopping 20 billion galaxies, giving us new insights into the universe like we never have before. The Rubin Observatory is named after Vera C. Rubin, who was a woman scientist in the 1970s. She was able to find the first direct, convincing evidence of the mysterious dark matter that I just talked about. She studied how galaxies rotate and found that galaxies were rotating a lot faster than predicted. In other words, there must be some sort of invisible glue keeping these galaxies together so that they wouldn't fly apart. That glue was later confirmed to be dark matter. One of the main missions of the Rubin Observatory is to study the mysterious dark matter. And for that, it is a wide, deep, and fast survey. This means that the survey is wide because it will be spanning large swaths of the night sky. It's deep because it will be looking at the faintest galaxies. And it's fast because it will be able to track those changes over time. The Rubin Observatory is not the first wide survey, nor is it the first deep survey, nor the first fast survey, but it is the first to do all three at once. For this, we need a very powerful camera. In fact, the world's largest camera, which was developed just around the corner here at SLAC National Accelerator Laboratory. This camera is about the size of a small SUV, and it is incredibly powerful. In fact, its panoramic vision field of view is able to fit 7 full moons. And in fact, its resolution is so detailed that it could spot a golf ball from about 15 miles away. We were able to get a sense for how incredible this telescope could be with the first look image, released around this time last year in June of 2025. As we zoom out of this image, we can see all of these little dots, each of which are galaxies. In this snapshot alone, there are over 10 million galaxies. We can see how galaxies are interacting with each other, with their push and pull of gas and dust. We can see a wide diversity of galaxies, from the elliptical to spiral to the irregular ones we spotted earlier in this presentation. And we can also see the incredible number of galaxies that Rubin Observatory will be looking at. This image was generated over the course of 7 days. But other than producing these incredibly gorgeous wallpapers, the Rubin Observatory's main goal is to carry out the Legacy Survey of Space and Time, otherwise known as LSST. This is a 10-year-long survey that will produce the greatest time lapse that astronomers have ever seen. It will be scanning the entire southern night sky every 3 to 4 nights. And in doing so, will collect over 20 terabytes of data per night. And if I haven't impressed you already with all of the specs of the Rubin Observatory, here's a really cool fun fact. The amount of data gathered by Rubin Observatory in its first year alone will be greater than that collected by all other optical observatories combined in human history. So we've built the world's most powerful telescope, able to produce a wide, deep, and fast survey over the next 10 years. Now, technically, more data should be a great thing. But now we're in a new problem, which is the big data problem. Because of all of the galaxies we'll be looking at, astronomers expect over 10 million alerts per night. That's just like getting a ton of notifications on your phone. So how can we tell what is interesting and what is not? Our solution is to have machines learn the universe. For the rest of this presentation, I will be delving into 2 facets of this. The first is how do machines learn? And the second is how are machines learning our universe? Let's start by tackling that first question. How do machines learn? For this, let's start with a simple example. How does a machine identify what a hand-drawn number is? It turns out that humans are pretty good at this. We have a visual cortex with millions of neurons and billions of connections that are able to spot patterns like this really easily. For our neural network, we need to start out with an example image shown here. This is a hand-drawn number that is 28 pixels by 28 pixels wide. We can flatten this image into a 1D array, creating 784 pixels in a list. This is the input layer for a very basic neural network. These neural networks are modeled after the neurons in our brain. It starts out with the input image here and makes a prediction about what the number would be. In between here is a very important intermediate layer step. These intermediate layers help us deduce what patterns can we look for in the numbers. And they do that by identifying smaller parts. For instance, one of these intermediate layer neurons might be asking, is there a hook at the top of the number? Which you can see exists in this number 0 here. This neuron here might be looking for a hook at the bottom of the number, which exists in this 0 here as well. But what about this neuron, which is looking at sort of a pointy edge, something you might see in a number 1 or number 4? Unfortunately, this one isn't in that number 0. As you may expect, some of these parts may be more important than others. For example, a vertical part, like a vertical line, may not be able to eliminate as many numbers, since that part is present in the numbers 1, maybe 2, 5, 7, and others, versus a curve at the lower bottom may actually be able to eliminate to just 0 and 9. For our neural network, we start by having one example. We have the machine take a guess, and over time, we need to train on millions of examples. When the computer first makes a guess, it does a pretty terrible job. But what we do is that we give the neural network a mathematical nudge. This is known as backpropagation. It adjusts the importance of these weights in the center for the intermediate layer, saying, hey, take less of a look at this part of the number and more at this part of the number. And ultimately, it adjusts until our model is completely accurate. And now we are able to feed in any example and deduce what the digit would be. So now we've looked under the hood. We've seen how a neural network is basically able to determine what a hand-drawn number can be. And you may assume that we could take this a step forward and then look at how to classify galaxies, for example. And so to pose the question, how are machines learning the universe? We're going to be delving into two really exciting features of this. The first is confirming what we do know, and the second is discovering what we don't know. Let's take a look at the first part, confirming what we do know. Earlier today, I asked you, what type is this galaxy? And just like the Galaxy Zoo volunteers, we were able to classify that into spiral, elliptical, and irregular. Computers are pretty good at doing the same thing with neural networks. You may be wondering, why are galaxy shapes so important anyways? Why is it so important for us to be classifying all these billions of galaxies at scale? This brings us to one of the core science goals of the Rubin Observatory, which is to study the shapes of galaxies. It does this by studying the structure of that mysterious dark matter I talked about earlier. This has to do with the phenomenon known as gravitational lensing. Einstein made a prediction that when you have a large body of matter, light eventually bends around that matter. For example, here we have the Earth shown here, and a distant galaxy, and in between is a galaxy cluster containing hundreds of galaxies. As the galaxy's light reaches us, its light bends around, and when it arrives at us, we get an image like the one here on the right, where we see a very distorted galaxy image. And it turns out this works not only for visible matter, but also for invisible matter. And by using this gravitational lensing method, we can then deduce the structure of dark matter in the universe. But beyond galaxy shape, what if we wanted to ask more complex questions, like how far is this galaxy? Was this galaxy forming stars? And what is this galaxy's mass? For this, we get to use a phenomenon known as redshift. This allows us to use the galaxy's color to determine its distance. The fabric of the universe is actively expanding. And so when a light is emitted from a distant galaxy, that light is also stretched out on its way to us. Longer wavelengths correspond to redder light. So galaxies that are further away end up looking redder. We can use this phenomenon for our advantage for a neural network model. Let's say that we have a bunch of examples here of galaxies, all with their known distances. This is also known as a supervised learning model because we start out with an answer key. These galaxies each have their known distances to them. For example, this galaxy here is 3.4 billion light years away. That means that its light has taken over 3.4 billion years to reach us. If we were to feed this into a neural network model, we can then make a prediction for what our unlabeled image would be. For example, an image that we get from the Rubin Observatory. This helps us determine what the distances to these distant galaxies are. And color is also important, not just for measuring distances, but for also knowing every single property we need to know about Rubin galaxies. The ultimate goal is to create a giant spreadsheet where we have the galaxy and its properties including its mass, star formation rate, distance, and more. However, we're faced with a major limitation, and that is the type of data that we are collecting. It turns out that many observatories, including Rubin, gather photometric data. This means that we are gathering light in a set number of filters. This is almost like looking at an image in just red and blue instead of the whole world of color. In the ideal case, we would get spectral information. That shows us what the energy is at every single wavelength and gives us the complete information about the galaxy. However, this process is much slower. It would take hours per galaxy to gather this data versus seconds for this data. This means that, unfortunately, we have to piece together what's missing based off of this limited information. But scientists have now found that computers can help us fill in those gaps, allowing us to achieve that complete information that we may be missing before. In this study done by Wu and Peek in 2020, they were able to feed a neural network a bunch of images of galaxies and determine what its entire spectral information would look like. And to emphasize how important this is for galaxy scientists, we can see how we can predict an entire history of a galaxy from just its spectral information. For example, here's the spectra of a star-forming galaxy, And here's the spectra of a quenched galaxy, or a galaxy that is no longer producing stars. For a star-forming galaxy, because it has those young bright stars, you see peaks in the emission lines as these bright stars are producing a lot of energy. On the other hand, for our quenched or our dead galaxy, the old stars are absorbing that light. By comparing and contrasting these two, we can actively tell which galaxy is forming stars right now versus what galaxies are not. But this is also important because each of these different spectral lines represents different stellar populations, and scientists have a pretty good grasp on all of these spectral signatures. In other words, spectra are like the fossil record of these galaxies. And by piecing together what star populations are active in a single snapshot, we can piece together the entire history of the galaxy all at once. So with the power of machines, we can help develop spectra and then extract crucial information like the galaxy's mass, star formation, and distance, allowing us to produce catalogs for Rubin galaxies. And of course, for a small subset of these galaxies, we are using ground truth validation, where a human further confirms that these results are correct for a small set. Catalogs are also important to help us build relationships between these galaxies and help us bring physical ties to the physics that we may be missing. This is showing the mass with respect to the size in what is known as the size-mass relation. It turns out that the location of a galaxy on this graph corresponds to the type of galaxy growth mechanism that is taking place, whether it's being dominated by star formation inside of the galaxy or by mergers as smaller galaxies come in from the outside into the main galaxy. By tracing these galaxy growth mechanisms, we can piece together how galaxies formed and evolved, which is one of the main goals of the Rubin Observatory. So now we've seen how we've confirmed what we do know by helping build these giant catalogs for the Rubin Observatory. But now let's get to the even more exciting part, which is discovering what we don't know about the universe. This comes down to finding anomalies in the Rubin data, or strange galaxies with physics that we don't quite understand. For this, we need a change of models. The existing supervised learning model that we used before doesn't quite work. Let's say that I have this galaxy here. This is a ring galaxy. It's a very special type of galaxy that is formed when another galaxy literally pokes a hole through it. We want to see more examples of these, and we want to understand why this happens. But if we were to feed this into our existing model, it would simply say, this is a spiral galaxy, and move on. Sometimes we don't always know what we're looking for, and sometimes we don't even have enough examples of these anomalies to create a whole separate class, one that can join the ranks of spiral, elliptical, and irregular. In that case, we need to use something known as unsupervised learning. For this, we can start with an idea that you may have seen back in middle school, which is finding outliers. So this is an example of a very basic plot with the X and Y axes, and we see that most of the points follow this general trend, but two of these points here are clearly outliers. We can do something similar with an unsupervised learning method, except instead of just plotting X and Y, we can plot all sorts of different things. We can plot the fuzziness of the galaxy, the brightness of the galaxy, the color of the galaxy, or in some instances, even plot every single individual pixel as a different axis. This is also called creating a high-dimensional space. And we can analyze this high-dimensional space as shown here. We find that galaxies that are more similar to each other tend to be more clustered together. And oddball galaxies, like the anomalies we want to look for, are placed further away from the more common types of galaxies. As this mouse is hovering over the different regions of this map projection, we see that galaxies that are more similar to each other tend to be more grouped together here. This allows us to find more examples of those strange anomalies we were talking about. To take another step back and look at another example, we can see how for James Webb data shown here, the different groups on this map represent the different regions in which galaxies are classified. For instance, for spiral galaxies here, they're all located in this general region. Elliptical galaxies are located there. Flat disks are here. And you can also see different variations of these galaxies. You may assume that galaxies that are more similar to each other would be grouped together. For example, a galaxy with smaller spiral structures versus more dense spiral structures will be located closer together than, say, a spiral galaxy and an irregular galaxy. But let's go back to our original search for ring galaxies. This is the original image that we started with. And these scientists, Mohali and Lochner, in 2024, were able to use that map projection method that I was talking about earlier in order to find 8 other examples of these ring galaxies, just by looking at what was nearby in that projection space. I also wanted to share 2 additional examples of how exciting this methodology could be. The first example is detecting strange events before they get weird. One of the advantages of the Rubin Observatory is that we will be able to understand events throughout time, giving us a time lapse of the night sky. But scientists need to follow up with these with further observations, allowing us to more detailedly track how an event changes in brightness. This is a really great example of how machine learning models can help. This is an event that was detected by the Zwicky Transient Facility, which is designed to track supernova events. In this instance, this is showing the brightness of this event over time. These scientists were notified by their machine learning model, which was then paired into their Slack messaging channel, that there was a weird event that was happening just around the corner. But when they took a look at the event, just up to this first blue line here, the event was incredibly flat. And so they were surprised that this was even flagged as an anomaly in the first place. But then, by following up with observations after its discovery date, the event suddenly dimmed in brightness, meaning that the machine was able to track these anomalies before it even happened. They were able to further look into the supernova and see that it was actually a very strange and rare physical event. And so, by being able to notify scientists about these events early on, we can track and change we can better understand through our observations how these events are changing over time. Another example of how we can use this method is through the anomaly match system shown here. This was a machine learning model unleashed on the Hubble Legacy Archive. It looked at over 100 million images, and for context, it would take a human centuries to go through that data. In the course of just 3 days, Anomaly Match was able to find over 1,600 anomalies, and out of those, over 800 of them were uncatalogued, meaning that they were not present in existing scientific literature. Some of these examples are shown here, and as you can see, they are definitely really weird oddballs. But this is just one example of how we can unleash these models on the Hubble Legacy Archive, an existing platform of data. But the Rubin Observatory, with its treasure trove of data, also introduces a new batch of data for us to look at. Furthermore, we are also entering an era of new observatories from the 2020s to the 2030s. This includes new telescopes like the Square Kilometer Array in the radio wavelengths, the Extremely Large Telescope, and the successor to the Hubble Space Telescope, the Nancy Grace Roman Space Telescope. All of these will be giving scientists a lot of data to go through, and that's where machine learning models can further help. I did want to wrap things up by concluding on what I believe to be is the future of astronomy. Earlier, I showed many examples where we could classify images, and for the Rubin Observatory, a lot of the data that we'll be getting is image data. But what if we were to ask questions about different types of data, like this photometric data here, or spectral data, or even light curves, which describe how events change in brightness over time? It turns out to a computer, all of these things look the same. It's almost like how you can ask ChatGPT in voice or in text, or even record a video and send it to ChatGPT. It turns out that our machine learning models can do the same. This brings us to the future of astrophysics, which is multimodal astronomy. Historically, we've had different telescopes do different things. We can have the Rubin Observatory look at visible light, the Square Kilometer Array look at radio wavelengths, or even gather different regions of the galaxy or spectral data. Scientists have had to put those all together manually to piece together a complete view of the universe. But now our computers are supercharged. It can cross-reference all of these types of data all at once, and we can ask our computers directly all sorts of information from these types of data. In other words, we'll be able to get a complete view of the universe like we have never seen before. And so looking forward, we do have a lot of data to play with the Rubin Observatory and the next generation of observatories just around the corner. And we also have a lot of science to do to carry forward the Rubin Observatory's core science goals and the goals of these other ones as well. The only question left is, what is there left to discover? I did want to wrap things up, especially for the students in the room, if you're curious about learning more about Rubin data or machine learning. If you're curious about getting started with building your own machine learning model, a really great example to start out with is Kaggle. They offer these massive data challenges, especially the plastic astronomical classification from the Rubin team. This was a challenge that was developed in 2018 before the Rubin Observatory, so that scientists could help build machine learning models before the telescope turned on. This was specifically looking at how supernova, or the death of stars, would change brightness over time. If you also want to take a look at publicly available data, the Mikulski Archive for Space Telescopes, NASA Exoplanet Archive, and also the Hubble Legacy Archive, which I talked about in this presentation, are all available to the public. And if you really enjoyed the exercise at the start of this presentation, it turns out that the Rubin Observatory and Galaxy Zoo, or the company Zooniverse, do have an official partnership. And as the Rubin Observatory continues to produce more data, we'll be able to help detect comets and sort out these stellar explosions if you'd like to help be a citizen scientist and contribute to one of the greatest citizen science projects there are. And I'd like to also end off by mentioning, if you want to learn more about the Rubin Observatory, there are some exciting events that are coming up. On Saturday, August 29th, Dr. Shreya Anand, who is part of KaiPAC, will be doing this really amazing science center exhibit where there will be immersive visuals and you'll be able to see the changing sky, or the transient sky, with the Rubin Observatory. And I also wanted to provide the QR code here if you want to learn more about KaiPAC events, although I'm sure many of you heard of it through this mailing list. We do have stargazing nights, which I also help volunteer at the Stanford Student Observatory, which is just around the corner. There will also be different public lectures on the rocky exoplanets, as well as summer physics programs, science fairs, and more. And finally, I'd like to end up by thanking KaiPAC as well as the Peninsula Astronomical Society for making this event possible, as well as the Los Altos Library. And if you'd like to learn more about the Rubin Observatory, please do check out these websites. Galaxy Zoo is listed here. And if you do want to reach out to me, feel free to do so through any of my contacts there. Thank you so much.
I'm sure those questions from the audience as well as online. We can start with the audience. And if you don't mind, repeat the question.
Oh, yeah.
So anybody back there?
Where is the data stored produced? All those terabytes.
That is a great question. I actually have a,
So,
And then that full.
yeah.
so the first question is, where is the data stored?
The second one is, where are the processing resources to provide all these models, all this giant amount of data?
The second question is, where are the processing resources analyzing the data?
Mhm. Yeah, that's a great question. I did want to showcase this slide shown here. This shows how Rubin transports data and creates alerts. This just started up a few months ago, so this is a very timely question. The way that Rubin transports data is that when it first receives the data from Chile, it actually delivers it to these different Rubin data centers that then process the data. This is an incredible quantity of data, so at each of these different centers, they are able to create the alerts for scientists to further interpret. And sorry, what was your second question again?
Where is the data processed?
Yes, so the data is being processed at these centers and then distributed to these alerts. And scientists can then access through the Rubin Observatory's websites these different alert information. But there's also Rubin Science Data platforms that is specifically designed for scientists to analyze the data in the website itself so that they don't have to export that incredible quantity of data onto their laptops. I hope that answers your question.
With Galaxy Zoo, having done a lot of the foundational work in coding spiral galaxies, globular clusters, etc., what is left now that the Rubin telescope is here? What's left for humans to do, or citizen scientists, as you say?
Yeah, I mean that is a great question. I think there's been, in general, especially with the rise of AI, a lot of anxiety about the role of humans and what are scientists going to do now that these machine learning models are so powerful. At the end of the day, I think there's two parts. The first is that we need humans to further analyze the data, and the second is we still need humans to check the data. So the first part is that we need humans to analyze the data. We need humans to improve our machine learning models. But also, after classifying all those galaxies, we need to further understand what is the physics behind which these galaxies are formed or how did they evolve. That's sort of the missing step that humans can help contribute. The second part is that humans need to still check the data. As you may have seen with AI, machine learning models can still make mistakes. And a really big part that I would like to emphasize here is that as I mentioned earlier, these machine learning models also go through ground truth validation, which is where humans are able to check the data, especially for spectral data, which is really important for building those catalogs. And so there's still a lot of stuff for scientists to do. There may be a lot of space, but there's very few astronomers. And so there's still a lot of really exciting science that has been left open. And if anything, I think with the development of machine learning models, there's a lot of interdisciplinary collaborations that will be opening up very soon. Yeah.
We have a hand up online.
Oh, yeah, go ahead.
Eric?
Yeah, sure.
Can you speak to a little more about those? Are they?
Oh, sorry.
Models being used, or are there other special pre-trained models?
I was wondering if you could maybe, like, if you had a little bit more specificity on that, or like just how.
Are you using like OpenAI or Anthropic or Qwen or these other models, or is it, or do you roll your own?
Okay, yeah. So the question. Sorry, I realized I haven't been repeating it. So the question is whether we've been using like existing foundational models like OpenAI, Claude, etc. These AI models that you've been seeing, like Claude and OpenAI, for instance, are very different from the machine learning models that we're doing here. So for instance, like Claude and OpenAI are large language models. They are designed to interpret text and to basically predict what the next word would be in a sentence, and that's how you get these large chunks of text. On the other hand, the machine learning models that we are developing here also include ones that are specifically specialized to look at images. And in general, like OpenAI and Claude are these large companies that have developed these foundational models. But here we're sort of starting from first principles and developing our own neural networks, as we saw in the presentation. I hope that answers your question.
Yeah, we have a couple of questions online. So Eric, if you
Oh.
want to unmute yourself.
Sure, thanks.
Oh.
I have a question about, are there any confidence metrics that go along with the AI outputs when it gives you, some new finding or some new, when it finds something new, can it tell you something like, I'm 90% confident this is this thing, or I'm 50% confident, or something like that?
Do I have to repeat the question, or
No,
I was gonna, yeah. Yeah, so that's a great question. Well, I don't know if you were able to see on Zoom, but when we started out this presentation, I asked everyone to raise their hands. There was still a little bit of debate from people regarding what the galaxy classification was, right? Similarly, Galaxy Zoo also counts the votes of people who are voting for different features that they see in the galaxy. At the end of the day, all of this has to do with probability. Even when we were predicting the digits that we showed earlier, the numbers that we're getting out isn't just, oh, this is a 0 or this is a 1. It's actually assigning probabilities to these numbers. And so you may assume that in certain instances where a model is not as certain, the probability might be like 50-50 between like two classifications, for example. And so by using these probabilities, that's also a really great way to follow up with further observations from humans to further confirm whether an event is an anomaly or what classification it belongs into.
Okay, and we have, sorry, one more question from Michael online, and then we'll come back to you guys as well. So Michael?
Yes, so it's obvious that the machine learning is going to enable you to do a lot of classifications of things. but how is that going to be curated to put out things like astronomers' telegrams? You still got the problem with millions per night. Is there going to be some way to sign up to say, I just want to look at this type of thing and ignore everything else?
Yeah, that's a great question. Well, for starters, the Rubin alerts offer many different streams. So for instance, if you are an astronomer that's studying supernova or the death of stars, you can subscribe like specifically to that stream. That being said, I definitely would encourage that because there are still millions of alerts that take place per night. The thing about these neural network models is that it helps whittle down the number of notifications that the Rubin Observatory would spot. Our night sky is changing very frequently. And so with all of those notifications, that is definitely way too overwhelming. With these machine learning models, we can help pick out what is important and what might not be. For example, it could point out an anomalous event that may be indicative of new physics.
Thank you.
Mhm.
Yeah, you showed an example of the photometric data,
Mhm.
sparse, and then inferring spectral data,
Mhm.
a full spectral set off
Mhm.
of that. Does that same methodology work for like structural data? So if you have low resolution data, or you haven't just collected enough data for, to be able to resolve it very well, can your models also say, oh, actually, I can tell you that that fuzzy blob is in fact a spiral galaxy, even if that information is not present in the original data from.
Yeah, that actually brings me to a really great example with the plastic astronomical classification project. So one of the goals of this mission of this project was that they provided these light curves, but these light curves showed how the brightness of a death of a star would change over time. So as you'd assume, it'd go really bright and then it would dim over time. The thing about the data that they provided was that it had gaps in it. And that was important because when the Rubin Observatory is scanning the night sky, it's doing so once every 3 to 4 nights. And so by the time it comes back to another event, there's going to be a gap in that data. One of the reasons why this challenge was introduced was to help develop machine learning models in order to sort of see how we can fill in those gaps in time, for example. So I think that was sort of what you were getting at, if that's correct.
That's one aspect of it.
Yeah.
Is if some, there's a galaxy that is just like so far away that we only get so many photons from it. Can we infer its structure based off of a sparse amount of photometric data?
Yeah, there's a way to do this also without neural networks. So one really great example is when we're looking at the earliest galaxies of the universe, and we are only able to look at James Webb filters that are maybe like 3 or 4 filters, for example. There's this methodology known as spectral energy distribution fitting, or SED fitting. It's a way that we can sort of fit the spectra to a very limited amount of information and be able to determine the properties of the galaxy from that way. And that's been around long before neural networks have existed. That was a lot of questions. Yeah.
You decide.
Oh, yeah, maybe this side.
So the Rubin Observatory has been functioning to some degree for around a year now, but I sense that it's not in really production mode yet. Can you comment on that?
So the Rubin Observatory has been operating. So since its first image in June of 2025, if I recall correctly, it started getting some first data in October of 2025, and now it's fully operational and creating alerts. Yeah. Yeah.
So can we sign up for alerts?
That's a
People in the peninsula, can we sign up for alerts?
That's a great question. I believe that there is a way to access it on the Rubin Observatory website. Oh, I don't know if you had anything to add, but if you go to the rubinobservatory.org, they do have a lot of resources available. I think that there is a way to like access all of the alerts and their specific subcategories, whether you're looking for asteroids or whether you're looking for supernova or changes in galaxies.
I assume that there's other observatories in that group that you said that they're looking at this intensively and they will go look at something's interesting, they'll point at it.
Yeah, a really big part of the Rubin Observatory's mission is to have like these follow-up observations by other existing observatories as well.
And I guess the other question would be, do we have to buy telescopes anymore?
Well, I think there's a lot of benefits of having like, your own telescope. It's a lot of fun to look up at the night sky. Yeah. Oh yeah, go ahead.
And I have 3 questions. So
Okay.
the first one is, well, we are like a blind man right now and studying all these abnormal galaxies and just whatever throw into our microscope or telescope. And now, what is the goal? Like, one question is it possible someday we discover the overlapping with another universe because we are studying the galaxy zoos? And we might be able to actually detect the part of the wheel. Now, when you're studying the zoo or many different galaxy zoos, is it possible to see the overlapping with another universe? That's one question. The second question is.
So just handle one question at a time.
Yeah, I'll answer the first.
So you want to take a stab at repeating it? Can we see another connection to other universes?
Yeah.
Through using the Vera Rubin?
Yeah, is
data?
it too far away to think about, or is the Rubin project strong enough to go ask that kind of question?
I think there's sort of two parts of this answer. The first is the idea of the overlapping universe, and the second is the depth of the Rubin Observatory or how far away it's able to look. So the first is the idea of an overlapping universe. So far, there has been no confirmation that there are multiverses. And so there really is no like border to the universe, if that's sort of what you're getting at. And the second thing is the depth of the Rubin Observatory. So I mentioned earlier in the presentation that it is a very deep survey. It's able to look at redshift 1 to 2, which basically means that it's able to peer back into like 10 billion years in the universe's history. But that being said, it's not deep enough to look at the first galaxies, for instance. So the Rubin Observatory is incredibly powerful, but it's not able to look at incredibly faint objects like the first galaxies that we saw with the James Webb Space Telescope. And so in that case, the Rubin Observatory is not as deep compared to the James Webb Space Telescope, but it is beneficial for many other reasons, but like providing a wide survey and providing a survey that tracks changes over time. Mm-hmm.
Thank you. So the second question is, now the reason, we are now surveying all these different galaxies to figure out the true nature of dark matter, dark energy, because we have no clue about them.
Mm-hmm.
It's helping us to understand that. Now, is it going to help us also to, to run into that string theory to see the 11 dimensions? Would that help us, to see a different depth of the universe because we learned so many different galaxies?
So
Mm-hmm.
try and take a stab at repeating the question. So in addition to analyzing dark matter, will there be enough information from the Vera Rubin observations to tie it into string theory?
Yeah.
Mm-hmm.
And the 11 dimensions, being developed by the theoretical physicists.
It depends on which one you talk to. Sometimes it's 11,
Yeah.
sometimes it's 12. But
Right.
yes, but
Like that, yeah.
I do have to admit that like string theory and like theory of physics is a little bit out of my area of expertise. But if I do recall correctly, string theory ideas have been very long debated. But the Rubin Observatory will help us constrain different properties of dark matter. And it turns out that the properties of dark matter are very closely intertwined with its particle properties. So for example, the way that dark matter interacts with each other also depends on how it behaves at a particle scale. And I think that's one of the most exciting parts about the dark matter question is that it's something that spans from the cosmological to the particle scale. So the Rubin Observatory may not be able to directly shed light on the on string theory specifically, but it will be able to hopefully provide insights that can bridge the particle physics and cosmology groups together.
Thank you.
Mhm.
And the third question is coming back to planet Earth. And as you know, whatever knowledge we accumulate is about how can we use it and apply it in real life, Like I know you guys are focusing on research
Mhm.
and even stay out of the real life. in some way. But now I work at Stanford too, before. We are always thinking about how do we use our knowledge in our real life. So would you guys provide any, knowledge for the real world? Is like, for now on Earth, because of AI, we're so lack of rare metals. Everybody's chasing after rare metal. And as you know, supernova supply a lot of heavier elements beyond the iron. And that's where the reason. So for your survey, you might have a lot of data like which galaxy has more rare metal, where to mine those rare minerals, all kind of things for the real world.
I'll take a stab at summarizing the third and final question. Are there any applications beyond astronomy that would come out of the Vera Rubin work that's being done? Real life applications beyond astronomy.
I think this is a very deeply philosophical question, right? Like, why do we do science? Why do we study space? So I guess I can sort of structure this in a few ways. I think the first thing I'd like to mention is some of the technological benefits that the Rubin Observatory has given us. The second is maybe a more philosophical answer about why we do science. And the third is maybe a conversation about like the rare minerals, because one of the things that the Vera Rubin Observatory is looking at is asteroids. So so the first thing is the technological benefits that the Rubin Observatory will give us. Doing science also means that a lot of these discoveries can translate into technologies that can directly benefit humans. For example, every year NASA releases this giant guidebook showing how its technologies have directly benefited humans, such as helping develop radar for planes or helping transportation and so forth. And many of these spun off into different startups, for example. I think it's incredible that we were able to build the world's largest, most powerful camera to look at galaxies. And for that, we needed a lot of innovations in the optic sphere to pack all of those optics into a car-sized camera. So the second part of this is maybe a more philosophical discussion, which is, why do we do science? I think this question can be easily applied to many different areas of humanity, right? For example, for instance, people like listening to music, even though it may not directly benefit humanity. People like watching sports, even though it may not directly benefit humanity. In a similar way, science is basically furthering humanity's knowledge. And I think that is a very important goal and a mission of humanity to come together as an international collaboration, as we saw here, to carry out a mission that is so much larger than our planet. I think it also helps us feel very small and very united together, especially during a time like now. And I think finally, to sort of make a comment about the rare earth minerals, one of the exciting missions of the Rubin Observatory, which I didn't have the chance to talk a lot about, is the discovery of asteroids. In fact, after the first look image was revealed, you can also go on the website and see a time lapse of all of the different asteroids that they were able to discover in just the first week alone. In fact, I believe over the course of the entire Rubin Observatory mission, they will be able to find millions of asteroids and near-Earth objects. Some of these may be a little bit concerning because they are so close to Earth, but it will help us give us insights about asteroids and these little smaller bodies in the solar system, and maybe even provide insights into the presence of rare earth minerals as well. Yeah, I hope that answers your 3 questions. Yeah. Mm-hmm.
We want to make sure some of those asteroids don't. So please, yeah.
All right. So is there like gonna be a regular cadence of when the big announcements are released? Like when can we expect like some of this new knowledge that's coming out of all this pipeline stuff to be shared with the public?
Yeah, that's a great question. So if you go to the Rubin Observatory organization website, they do regular public press releases where they summarize the results that are available for people to look at that span all sorts of different sciences. So if you go on the news website, they have updates there. I also remember seeing on some of their social media platforms, they do like to announce some of like the smaller discoveries as well and share what the Rubin Observatory has been looking at. Mm-hmm.
I was thinking of reading a part of it was Sky and Tulsa at 8. they talk about the application, they have pretty much want this line. Applying it to a particular type of galaxy, all galaxies. And the software, after going through lots of data, did identify maybe 30 or 40 of them. They look like species, but they really weren't. If you looked at them. So there's kind of a false positive. So that was only determined by people with enough experience to tell the real thing from something close. How do you deal with that? There's always going to be some movement. Eastern Albonia that comes up with some new discovery. How is it going to be vetted before we all get subject to it?
That's a great question. Yeah.
Repeat the question is there some other process by which we vet the findings using perhaps astronomers or some other individuals who vet and certify that the information is accurate?
Yeah. That's a great question. As I mentioned before, one of the biggest parts of using neural networks and machine learning is ground truth validation. But to specifically talk about the example you gave, I actually had an additional example here that might be interesting for you. So this was done by Kate Story Fisher, who is actually now a student at Stanford. But this was done back in 2021. And this is sort of showing that like distribution of galaxies that we saw earlier with the unsupervised learning method. And one of the things that they were looking at were these different anomalies in the data. They were able to find some anomalies here, but only after that they were able to follow up with spectral observations. So basically pointing at the telescope at this galaxy for hours at a time, were they able to finally confirm that it was actually an anomalous event. And so I think a really important part of this puzzle is also having those follow-up observations that can provide us more information and more data about an object and helping us confirm that the machine's flagging method actually flags a real anomaly.
For the data processing, for the future data processing, would you say that it will rely more on software breakthroughs or hardware breakthroughs? For the software, it's more like algorithms and the models, and then for the hardware, it's like the data was run and the models.
So I'll try to. So how is the data going to be processed using software and hardware?
Or like, is it more specifically like, would we see more improvements in software or more improvements in hardware?
Okay.
That is the $1 million question. I mean, it would be really great to know. Yeah, no, it's a $1 trillion question. It would be really great to know which one would be advancing faster or which one we should focus more on. That being said, I think I'll kind of give a non-answer by saying that there are a lot of exciting developments in both. There are a lot of really creative ways to look at neural networks and also a lot of creative ways to do pre-processing of that data, which I didn't have the chance to go into here. For example, when we have limited information, there have been a lot of creative ways that scientists have been able to augment or increase that amount of data for our neural network models. There have been a lot of different model architectures that look at different parts of the galaxy image or even are able to track the galaxy changes over time using things like attention and memory within the neural network. When it comes to hardware, on the other hand, there are certainly a lot of developments taking place in that space. Actually, just the other day, I got the chance to talk with the founder of Cerebras. If you do not know this already, they recently went public and were able to make a lot of money by providing these giant GPU chips, which they believe will be a direct competitor to NVIDIA. And so after talking with him, it seems like there's a lot of exciting developments in that space. But that being said, I think the only way for astrophysicists to truly benefit from this really exciting wave of machine learning is to be riding on both of those waves, right? Which is to be aware of the different types of model architectures that are out there, as well as the ability to use different types of GPU chips and hardware so that we can truly use all of the computing power available to understand the universe.
Does dark matter, does AI along with gravitational lensing currently help understand the structure of dark matter intervals and beyond rotation curves and the structure of
I would like to mention that we know even less about dark energy than we do about dark matter because dark matter interacts like with the gravitational force and we can see it as you mentioned, halos around galaxies. On the other hand, for dark energy, we know very little about its properties. But to speak about dark matter in particular, we can build maps of dark matter in the universe. And one of the goals of the Rubin Observatory is to help understand the structure of dark matter in the universe. These neural networks, by analyzing millions of galaxy shapes, and especially their distortions as that light bends around the dark matter on its way to us, can help us understand those better. The example that I showed with the gravitational lensing was a very severe example where we literally saw the galaxy arching around the galaxy cluster. But in most cases, the changes that we see in the galaxy shape are incredibly minor, which is where the neural networks come into play. They can help spot changes that humans literally can't. And they can also see the shapes of dark matter clusters and clumps in the universe. Mm-hmm.
So I was just going to ask that with the ability to track changes over time, as was mentioned, would we have models analyzing those too and look for anomalies in motion, which might say something about dark matter?
Do you want to repeat the question? I think you've got it.
Oh, okay. Yeah, I think the question was about tracking anomalies that happen over time. Is that correct?
Yeah, changes over time. I mean, that anomaly identified, and maybe that all something insight into the dark matter because we see things moving.
Tracking anomalies over time, and how would that allow us to discover characteristics of dark matter in the universe? Yes. Thank you.
Well, one of the main missions of the Rubin Observatory is to track changes over time, like the supernova example that I mentioned earlier. When it comes to tracking the motion of galaxies over time, Rubin Observatory can help contribute to that because it will literally be able to see the changes of these galaxy movements. For example, one of the really great ways that this can be used is by understanding the movements of galaxies within galaxy clusters. As you may imagine, in a galaxy cluster, there's a lot of galaxies, and galaxies actually are formed in the center of dark matter overdensities. And so when you have a galaxy cluster, you can imagine there's a lot of galaxies and there's also a lot of dark matter. So that can help us provide a lot of insights into the properties of dark matter itself.
Yeah, I'm just wondering in the future, is there a way that we keep tying these in with different observatories? I mean, what's the plan going forward? This seems to be a great idea. So if we look to me, I got the impression it's a one-off. I mean, are we going to start getting other telescopes involved? Other ones that are just like today, there's a couple of them which we use just for observation, where we actually have a human looking in it. Are we going to retrofit those? Are we going to start feeding it? Are we going to have different I mean, is there a plan going forward?
Yeah, I mean, there is a lot of active research being done, especially even at Stanford, to help contribute to that multimodal astronomy idea that I was discussing about earlier. This is an idea that kind of came about, I think, a few years ago, and it's been really developed over the course of the past few years. For example, at Stanford, my PI, Professor Risha Weschler, actually spearheads this group that does like AI for Astro, where they're actively thinking about these questions. And I really recommend you check out the website if you want to learn more, because there's a lot of really exciting plans for this. In particular, the Vera Rubin Observatory is going to be providing us a lot of data. And so a lot of people are thinking about ways of how can we pair up this observatory's large quantity of data with the more specific or even in-depth information that we're getting from other observatories. So I think that is a really great question. And there's already so much active research and a lot of interest into the future of multimodal astronomy going forward.
You have one hand up from Eric. It's sort of.
Oh, yeah.
Sure. Sorry, me again. Yeah, this kind of blends right in with my question here. How close do you think these AI models are towards generating their own theoretical models for what they see? Proposing physics that might match the data.
That is a really great question. Actually, just before this talk, I read a research paper about how OpenAI was able to make a discovery about like one of these very unsolved theories in math about the location of points on a grid. I also know that in the past, like in astronomy specifically, there have been a lot of theories that have been answered with the help of AI. For example, some that have to do with rotating black holes, which are incredibly condensed and high energy systems that we know very little about. Um, and so hand in hand with AI, there could definitely be a lot of physics discoveries down the road. I think in general, the astrophysics community is definitely showing some degree of caution to make sure that these are very legitimate discoveries. But that being said, I think it is a very exciting sphere to be thinking about. And I really appreciate like that you asked this question because I think it's very timely, especially now when we're hearing about all of these theoretical discoveries taking place in math and in science in general.
Thank you, please. We're going to skip back to the previous question
Mhm.
for this one. Could you put the Rubin in the context of all the great observatories that are under construction or the web that's out there, the Nancy Grace Roman, the super large telescope that's also being built in Chile, Mauna Kea, and so on? Yeah, how do these programs integrate and where are they going in the future?
Yeah, that's a really great question. So I'll try my best to answer this question in depth. So the Vera C Rubin Observatory, as I mentioned before, is a wide, deep, fast survey. Its goal is to produce a time lapse of the entire southern sky every 3 to 4 nights. The extremely large telescope, on the other hand, is more similar to James Webb in that it will be specifically looking at targets that scientists choose. In fact, it will be able to resolve incredibly small galaxies, some of which are the earliest first galaxies in the universe, meaning that it will be able to peer deeper than the Rubin Observatory, but only for a smaller set of targets. The square kilometer array is a radio telescope. So unlike the optical wavelengths and the infrared wavelengths being used here, this is a whole different set of wavelengths that are being explored. The Nancy Grace Roman Space Telescope is the successor to the Hubble Space Telescope, but if I recall correctly, it has a field of view that is around 100 times larger than Hubble. And it will be launched in space. So another big difference between these is that these are ground-based observatories and that is a space-based observatory. I hope that answers your question.
This data flow, the idea flow, go between the various different types of observatories. You're coming up with millions of events per night over 10 years of looking at the southern sky. How is this focusing other people's, as well as the neutrino observatories, the ice cube? How is this focusing other people's, research projects or jumping at the opportunities that arise by chance, by unexpectedly?
Mhm. Yeah, I think it's a really exciting time to be working in astrophysics. If you read basically any paper in the astrophysics community right now, a lot of them have a conclusion saying, with the era of new observatories, we will be able to do X, Y, Z. And so, if anything, a lot of scientists are thinking about the future once these observatories turn on. That being said, a lot of these are working independent of each other, but that doesn't change the fact that all of these are international collaborations. They involve many countries coming together, scientists from many countries coming together to make these telescopes possible. And so you may imagine that even though these are all separate observatories, there are a subset of people who are working on very similar questions that want to use the data from all of these telescopes. And also the broader astrophysics community is extremely excited to be using all of this data all together. And so even though they may be separate, the chance for collaboration is incredibly high moving forward.
How does the current political climate and this anti-intellectualism, this destruction of budget, and education, the astronomical community, and the work you're doing and how?
Well, currently I am an undergraduate student, so I think or master's student, so it's a little bit different. But I would like to comment that yes, it is definitely a very challenging time. If I recall correctly, the Rubin Observatory has been delayed a few times because of COVID and also because of funding challenges. And there have been many times where many of these telescopes and others have been threatened by some of these budget cuts that we've been seeing. In addition, there is the also more direct threat that is seen by students here at Stanford, which is the budget cuts to different grants that are sponsoring this research. That being said, there are a lot of challenges and also a lot of discussion on how to move forwards. For example, there is a company that I talked to recently that is thinking about having observatories be more privately based. They're planning to build a private-based observatory, which will provide a lot of smaller telescopes, allowing more scientists to access these smaller telescopes all over the night sky. That is one example of how scientists are adapting. But in general, I think the fact that we were able to piece together the Rubin Observatory and that there is so much international support for this types of exciting science means that there's a lot to look forward to as well.
So I'm gonna say this is the end of it, but people are welcome to stay and ask additional questions. So with that, I just want to say thank you again.
Right.